Okay, day 108, making and hearing sounds. The medium, that is the material that's vibrating. Material that vibrates in order to pass along the sound wave. Vibrates. This messy thing right here is vibrates. Area of compression is where the air molecules are closer together than normal. That's where the air molecules are closer together than normal. The area of rarefaction then is the areas where they are farther apart than normal. What makes up a sound wave then is this pattern of vibrations in air molecules. I will try to straighten it up then. You're all about that. I'm going to say in letter D here, patterns of vibrations in a material, because sound can travel through solids and liquids and gases. And it's a pattern of vibrating closer together than farther apart. Closer together, farther apart. So today, we're going to understand how our ears detect sounds. Why we have sounds that are different from each other. And it's just good to know how your body works. Something that we think that everybody should know a little bit about, at least. You're going to name and describe parts of our ears by the end of this lesson. We have a little bit of homework. It's not 107, it is homework 108. And we have a quiz, I guess, next Tuesday, maybe? Yeah. Okay, let's look at this video here. Hours of rising shepherd tone. A little bit of a magic trick, sort of. We have a pitch that's going up. How high can it get? If it goes on and on for 10 hours, going higher and higher, if this goes on for 10 hours higher and higher, there should be a point where we can't hear it anymore, right? Because it's too high. Jose, please put away your phone at this time. Let's do science. Let's fast forward to the better parts. Now let's fast forward a little bit more. Let's fast forward some more. That's a really good part. It's only going up, it sounds like. It only sounds like it's going up, yet somehow for 10 hours it just keeps on going up. Yet, how does that all work? Interesting. Here's the answer.
I was reminded of it this week by FallingFallings.com. Hey, Vsauce, Michael here, and today I released a brand new Vsauce Lean Back, a playlist of educational videos from all over YouTube that I think are cool, and I host sort of like a Vsauce TV show. You can start that by clicking the box up in the corner or the link at the top of this video's description. But before that, I want to talk about the shepherd tone. It's a sound made out of multiple sine waves that play a trick on us. See, what they do is continuously rise in pitch, and then every so often one of them drops down an octave. But our brains don't perceive that because the other two continue rising and cover for it.
So when we hear that video for 10 hours, we're actually hearing 3 different tones at the same time. They're all rising. One of them, when it gets too high for us to hear, that one jumps down lower, but the other 2 keep on rising at their lower octaves.
The sine waves take turns dropping down an octave, producing a sonic barber pole, a noise that appears to keep rising in pitch forever and ever without ever actually going anywhere. I was reminded of it this week by FallingFalling.com, a creation of internet artist New Raphael, where the shepherd tone seems to go down and fall forever. Raphael also made some other cool sites like OutInTheWind.com. Here, there's nothing except for this menacing wind that slowly erodes your cursor. Okay, now some of you may already...
Okay, enough of that fun and games. Okay, the parts of our ear that detect those things. The flappy part outside your ear is called the pinna. Sometimes it's called the auricle. That apparently helps to capture sound waves and focus it down the ear canal. That's this thing right here. Ear canal. There is some indication as well that all the little grooves and surfaces of the pinnae, auricle, whatever you want to call it, all those grooves and bumps help us to determine if a sound is coming from above us or below us. I'm not sure how that would work, but I read that once many, many years ago. Okay, so sound waves go down and then they hit this membrane right there called the eardrum. And if you're not careful, that can get punctured. So that's why they being doctors, suggest you do not use Q-tips to clean your ear canal. You might actually poke that. By the way, there's wax in your ear canal, right? It can get kind of gooky in there. They think that perhaps maybe that wax is there because it helps keep critters out. Little buggy things don't like that wax. Maybe it's also to help keep this moist so it doesn't dry out and crack. That's also a possibility. Every once in a while you might get hearing problems. You might have muffled sounds. You can't quite hear clearly. And that's because the earwax is built up and is blocking the eardrum. I've had that happen a couple times. I went to the ear doctor and he says, "Oh, let me just help you out with a..." Pulled out some tweezers and he pulled out some wax from here. It looks a little bit gross. And I asked him, "What in the world can I do about this?" And he says, "Not really, not much of anything. It's just come on in every few years and we'll take care of it." So it's a natural thing. Don't get all freaked out about it. There are some drops that you can get at Walmart or other kinds of drug stores, and you just sit with your head to one side and you soak it there for, let's see, I guess you put it in before you go to bed, and in the morning you rinse it out in the shower. That kind of a thing. That helps clear out the wax if you want. Okay. I'm not exactly sure what the name of the chemicals are that I'm thinking of. I know it's not bleach. You don't put bleach in your ear. That's for sure. Okay, next. Let's see here. We have these parts right here, which are called the hammer, anvil, and stirrup. Hammer, anvil, and the stirrup. Those are these little bones right here, and they have the shape of, sort of a hammer, an anvil, and a stirrup. Those are little tiny bones. I believe they are the smallest bones of your body. Connect. Oh, yep. Hammer is first. It's right here, this one. And then this part right here they call the anvil, and then this last part, stirrup. They actually kind of have the shapes of those items. There is a name for the three bones together. I forget what it is, though. And then we have this snail-shaped thing. That is called the cochlea. Cochlea, C-O-C-H-L-E-A. It's sort of like a shell-shaped. It is hollow. There is liquid on the inside with little tiny hair-like cells. They're not exactly hairs, but they look that way under the microscope. And then we have the auditory nerve. Auditory nerve. Okay, now then, those are the exact little parts. All of these parts on the outside, the pinna, ear canal, and eardrum, are called the outer ear. And then the three bones together are called, with the cochlea, are called the inner ear. These things right here, these arches, they are in three different perspectives. One goes up and down, one goes sideways, one goes forward and back. They are also liquid-filled with little tiny particles that float around and nerves. And from how they are floating, we can tell if you are leaning forward, backward, left, or right. Max, please put away your phone at this time. Let's do some science. Okay, so vibrations of the air come and they hit the eardrum and make it vibrate. That makes the hammer vibrate. Then the anvil vibrates. Then the stirrup vibrates. Then the outside of the cochlea vibrates. Then the liquid on the inside vibrates, which causes the hair-like cells to vibrate, which stimulates the nerve that goes to your brain. What's the range of frequencies that people normally hear? I think I touched upon this last lesson. The low pulses are about 17 hertz. 20 hertz is a common thing to have written down. Up to 20,000 hertz. Not everybody can hear up to 20,000. Some people can hear a little bit higher. Ultrasonic, then, is anything that is above 20,000. Ultra-high frequencies, super-high frequencies. Ultra means more than, so more than we can hear. Bats, dolphins, other kinds of critters that use echolocation use this. Infrasonic, infra means below, less than. Sounds that are lower than 17. And there's indications that elephants can do that. Activity, see how high you can hear. Okay, so this is where the wolf whistle comes in, the dog whistle kind of a pitch. Let's see here. Let's go to a regular website. What's this called? Plasticity. Plasticity. There we go. No, that's not what I wanted to see. Back up. Okay. Everybody can hear that. That's 440. Okay. Okay, now I'm starting to have a hard time hearing this.
Yeah. I don't want to hear it. No, go ahead.
I can't hear that.
I can hear it.
Now, it is a normal part of growing old. A normal part where the little tiny hairs that are inside the cochlea, they stop working well. Sometimes it's because you've experienced very loud noises that cause them to vibrate so much they actually break and they do not grow back well. Or it's just they get old and inefficient as the years go by. But you gradually lose the ability to hear that higher pitch. Let's see how high you guys can hear, though. Raise your hands when you can hear this. Everybody should have their hand up. And now let's go up. There is 8,000, 9,000, 12,000, 14, almost 15, 16, 17,000. Here, I'll stop it. Start. Can you hear that?
Yeah, I can hear that. Oh, wow. Oh, wait.
19,000.
That actually hurt. Start and stop. I just hear rolling. It's not even.
I'll start and stop it so you might be able to detect it.
Yo, that's what I can hear. I can hear a little. Like a little. Not anymore.
Okay. So, enjoy the ability to hear the high pitches while you can. If you want to preserve those kinds of abilities as long as possible, don't abuse your earbuds and don't expose yourself to loud noises for long periods of time. Okay, so rock concerts, wear earbuds. Those little ear foam things. When I went to a concert festival thing this past summer, I wore them and I offered them to my kids as well. You can still hear the concert just fine. They don't block out the sound completely by any means, but they make it a little bit more gentle on your ears. I highly recommend that. Okay, where do we leave off here? Moving on. What is tinnitus? It's the constant ringing of ears. Constant ringing in your ears. It might be a rushing sound. It has some other permutations as well, other variations, but it's usually either ringing or a rushing, whooshing sound. And it's all the time. What causes this? Repeated loud noises. Perpetual loud noises. My dad worked on a farm, so lots of machinery for hours on end. And he now has beep in his ears all the time. So I grew up in a household that had classical music playing a lot because that helped cover up the noises for him, made life a little bit more pleasant. When the iPods first came out, somebody sued Apple because he got tinnitus from listening to his iPod all the time. And he lost his lawsuit because he didn't follow the directions as to how loud to allow the thing to play music. How do you know if your iPod or other music device is too loud? Anybody know? If your ears vibrate, yes, that is a little bit too loud. Anything else? Two ways. Number one, if you cannot hear a normal conversation next to you, it's too loud. Or secondly, if other people can hear it, it's too loud. Is there a cure? Not really. There are advertisements on the web that claim that there is a cure for tinnitus, but there's also ads on the web that say, hey, take this one pill and you'll lose 500 pounds. It just ain't true. From the Mayo Clinic, paragraph 6A. Will, would you please read that about tinnitus?
A number of health conditions cause or worsen tinnitus. In many cases, an exact cause is never found.
Adam.
Common cause of tinnitus is inner ear cell damage. Tiny, delicate hairs in your inner ear manipulation. The pressure of sensitive triggers ear cells to release an electrical signal through the nerve from your ear, auditory nerve to your brain. Your brain interprets these signals as sound. If the hairs inside your inner ear are bent or broken, they can leak random electrical impulses to your brain, causing tinnitus.
Nate, 6C.
Other causes of tinnitus include other ear problems, chronic health conditions, and injuries or conditions that affect the nerves in your ear or the hearing center in your brain.
Chris.
In many people, tinnitus is caused by one of these conditions.
Christian.
Age-related hearing loss. For many people, hearing worsens usually starting around age 60. Hearing loss is caused by medical terms for this type of hearing loss is presbyopia.
That's exactly how I would read it too. Maddie, 6F.
Loud noises such as those from heavy equipment, chainsaws, and firearms are common sources of noise related to hearing loss. Notable music devices such as MP3 players or iPods also can cause noise related to hearing loss if played loudly for long periods. Tinnitus caused by short-term exposure such as attending a loud concert usually goes away. Long-term exposure to loud sounds is less common.
Okay, so sometimes people's ears don't work for one reason or another, but the brain still works in terms of the place that interprets sounds. And so they have this thing called a cochlear implant. It's a bionic ear. And it enables people who, for whatever reason, don't have working ears, they can still hear. So let's find a video here where they have somebody hear for the first time, or at least after a very prolonged period of time. So let's see here. Cochlear implant simulation on speech and music. Oh, I'm in the wrong thing. I wanted to be on YouTube. There we go. When you first get the implant, the brain is still trying to figure out how these signals are supposed to make or be sounds. And so for the first little while, this is how it sounds to the person.
What kind of bait do you use to catch salmon? What kind of bait do you use to catch salmon?
Okay.
I want to hear the actual music.
Okay. Let's see. That wasn't the video I thought it was going to be. Here's the one that I thought it was going to be. Activating a woman's implant. Activating cochlear implant. Let's see. Oh, I don't have the author or anything. I need to type in the address. This will take a moment. https://youtube.com. Watch equals BD0AZ9KSGAI.
Then I'm going to turn the volume up and up.
Okay, now this lady just got her cochlear implant. They're going to turn it on for the first time. She is not a person who was born deaf. Can anybody, I want to see if at the end of this you know why I can say that with great certainty. Anyway, she's going to hear her husband's voice for the first time. Yeah.
Because she can speak.
That's right. That's right. She can talk, so she has heard words before. When you lose your hearing, you end up having a very difficult time talking because you can't hear yourself, and so words start to get kind of mushed together. But anyway, she can understand other people talking, so obviously she's heard people talking. Okay, here we go.
Up and up until you hear my voice. Keep up. Keep it out. Okay, hang on. Hang on. Okay. I'm going to turn everything down. I'm going to take this down a little bit. Okay. Okay. Can you hear my voice at all? I want you to listen and see if you can hear my voice. Okay. You're okay. Are you able to hear the sound of my voice? You are? Okay. I'm going to pass these around because I knew you were going to need these. That's awesome. I know, you're going to sound loud. Your voice will sound loud. Been waiting for this day. Did you hear it? It's gonna make me cry. You sound very loud to yourself, don't you? You okay? Okay, I'm gonna turn it down.
You said you weren't going to cry. You're funny.
Your mama?
Did you hear what I said?
She heard your voice because she turned them up for you.
Oh, she did. Why is this quickly?
So if you remember, I told you when we talked about doing the surgery that it may sound like Donald Duck at home. By the time you get home and listen for a few hours, it's not going to sound as bad. The fact that you can hear my voice and your mom's voice is awesome. It's a big improvement from where you started at with this ear. Okay?
That noise gonna go away?
Mm-hmm. You'll notice it go away. It's more noticeable right now because you're hearing by an electronic way of hearing. So, yes. So it's sort of like this machine quality to the sound. It takes a little bit for your brain to adjust to the way this sounds. Once it does adjust, it will not sound like this. Today is the worst day. Okay? Every day it should get a little bit better.
Is the noise gonna go away?
It should go away, yes. It's pretty noisy on the first day. Okay. Let's see if you can hear your husband. Keep looking at me. See if you can say something to him.
I love you, Allison.
I love you. That's awesome. That's good.
Okay. You can see YouTube videos of little toddlers, little 3-4-year-olds who are truly hearing for the very first time. And that's kind of interesting to see. Okay. Now then, musical instruments. How do each type of instrument make lower pitches? For string instruments, pianos, guitars, violins, how do you make lower pitches? Some of you music folks. Wade. Thicker string. How else? Think about a harp. How do these different notes get made on a harp? Chris? Longer strings. Yep. Now let's say you're playing a guitar and one of the strings is just a little bit too high of a pitch. What do you do to it to make it a little bit lower? You don't make the string thicker, you don't make it longer. What do you do to a guitar string? Make it just a little bit. Ignacio? Loosen it. So thicker, longer, looser strings make lower pitches. Okay, pipes. Think about all the different instruments that use pipes. How do you get lower notes? Jonathan? In an organ, which pipes make the lowest notes? Not sure. Wade? Longer pipes make lower notes. The really, really tall pipes of an organ are the lowest ones. But those tall pipes aren't just tall. What else is different about those things?
The size.
The size, the width, yep.
And the opening.
Yep. A trumpet makes higher pitches than a tuba, and the pipes of the trumpet are narrower and shorter than a tuba. Man, they go all the way around somebody sometimes. That's called a sousaphone. And it's basically the same thing. Longer, wider pipes. I don't think there was anything else to say about that.
What about the openings of the pipes?
Yeah, that'd be wider too. Yep. Drums. Think of a drum set. Think about the different kinds of drums being bongos and kettle drums. Yep. Wider.
Some won't have the snare on them.
Yep. And I didn't know this until just a few years ago. You can tune a drum. I thought a drum was just a clickety-clack, pound, bang, bang. No, there are pitches to it. And you get a little key, and you can turn little parts on it and make the drum head tighter or looser. So wider, looser drum heads will have a lower pitch, and the membrane itself can be different thicknesses. So a thicker drum head will be a lower pitch. Oh, the depth of the drum, I bet you that also has something to do with it. I bet you. Good thought there. Okay, so with different instruments, we could have, let's say, a trumpet play a middle C and a flute play a middle C, and we can tell which one is playing which. They do sound different. Why? Why is... I'll get to your question in just a second, Nate. Yep. Why does a trumpet sound different than a flute or a saxophone? And the answer is because of overtones or timbre. It is, they play many frequencies at the same time, and the combination's a little bit different. They play different combinations of pitches. So when you play the middle C with a flute, there with that instrument you are only producing one pattern with a certain hertz, a certain frequency or wavelength that matches what we call middle C. When a trumpet plays middle C, it not only plays that wavelength, it also has some others at the same time. They're not as dominant by any means, but they're still there. And a saxophone will play the middle C frequency as well as a different set. And because of these different sets that go along with it, we can tell if it's a saxophone or not. The other difference is what's called the envelope. The sound is not a steady, constant volume, but rather there is the rate that the volume goes up to its maximum, and then after the tone is set, the volume dips down a little bit, holds steady, and then when you stop blowing or stop playing, then the sound goes down, but it doesn't go down at the same rate. In some instruments it goes down faster than others. So the attack is the increase in volume to a maximum. Decay is the decrease from a maximum to the normal level. decrease from the maximum to the normal level. Sustain is the normal level of the volume. And then the release is how quickly it disappears at the end. So here we have different instruments. A flute has a gradual increase, and then it stays flat for its sustained normal volume, and then a very quick stop. A guitar, though, you hit the string, and it takes a long time for that thing to get quiet. The string is vibrating for a very long time. Ignacio, we're not using the laptop right now. How about closing that up and looking at our science? So you can see the different kinds of volume changes with the different instruments, and we can divide all of those graphs up into attack, decay, sustain, and release. Alrighty, and that's the end of the lesson. In your Schoology, we have Homework 108, and we also have, I'm going to try something new and different, I'm going to try having the wrap-ups on Schoology as well.